Federal de Pernambuco, en Colombia, la Universidad Nacional de Colombia, la Universidad del Norte, en Barranquilla, en México, en Simvestab, y todo México, en Perú, la Universidad Nacional de Barranca y la Universidad Nacional Mayor de San Marcos. El día de hoy, Isaías Gonzaga de Oliveira.
I don't know. I think that my web my connection is not good. I didn't read. What did you say?
Well, Professor Pratap Kollu, can you hear now, Isaías? ¿Puedes escuchar ahora?
Yes, yes, I can. Now I can. Okay.
Yeah, actually, Louis' internet is a little bit weak, so I too can't hear. Don't worry.
Okay, yeah, don't worry. Okay, I will. El profesor Pratap Kollu es profesor en la Universidad de Hyderabad, en India. También su especialidad es materiales magnéticos, multiferroicos, lab on chips biosensores, exchange bias magnetic multilayer thin films, graphene magnetic nanocomposite. Estudió en la universidad, el PhD en la Universidad Nacional de Chungnam, en Corea del Sur. En la maestría en ciencias en la Universidad de Andhra, en India. Maestría en electrónica y física en la Universidad de Andhra, en India. Matemática, física y electrónica, su bachillerato en la Universidad de Andhra, en India. El profesor Pratap Kollu es un Newton Fellow de la Royal Society y ha sido representante en India en la Newton Fellow de la Royal Society de Inglaterra. Ha hecho también pasantías en Cambridge y lo conozco justamente de aquellos tiempos en Cambridge. El profesor Pratap Kollu maneja un buen financiamiento y hace colaboraciones con también los peruanos. En un proyecto está haciendo una colaboración con los peruanos. Pronto va a recibir a unos estudiantes peruanos, 5 estudiantes peruanos de la Universidad de San Marcos que van a visitar India. Y también está siempre dispuesto y feliz de colaborar con las universidades latinoamericanas en proyectos en conjunto. Bueno, la charla del día de hoy del profesor Pratap Kollu es Nanocomposite 2D Material Matrix for Battery Anode Materials. La charla va a ser en inglés y las preguntas pueden hacerlas en inglés directamente al profesor Pratap Kollu, y las personas que no hablan inglés por algún motivo, el público, el profesor Isaías Gonzaga de Oliveira va a hacer la charla del día de hoy, pueden hacerlas en inglés directamente. Bien, entonces, gracias por la atención. Disculpen la interrupción en mi internet, no está muy fuerte. Me encuentro en México, regreso a Perú el otro mes. Perfecto. Bien, Professor Pratap Kollu, let me introduce you the panelist. Professor Albino Aguiar is professor from the Federal University of Pernambuco. Professor Isaías Gonzaga de Oliveira from the Federal Rural University of Rio de Janeiro. Professor Arturo Martínez from Simvestab from Mexico. Professor Jairo Roa and Professor David Landinés are from the National University of Colombia. Representative from the National University of Barranca is Professor Ricardo Celis Santos. Professor Ángel Bustamante is not online now, but is from the University of San Marcos. Well, then we are going to, you can share your screen and you can start now.
So I used your poster only. Thank you very much. So the title of my talk is Nanocomposite 2D matrix for battery anode materials. And I'll give a flavor of my other researches also. So this is my affiliation. I am assistant professor in Center for Advanced Studies in Electronic Science and Technology, School of Physics. So I'm also a Newton alumnus research fellow at Cavendish Laboratory in the University of Cambridge. So until 2025. So this is my title slide, and so we are here. So we are here, and you are here somewhere. Correct me if I am wrong. So all of you are here. Maybe Peru and all these places are somewhere around here. So it is almost, I visited Peru in 2016, and it is a journey of almost 2 days. And so, of course, the journey is worth enough. It is a beautiful country and very nice people. So I enjoyed the trip. So this is where we are in India. This is the southern part of India, and we belong to the province of Telangana, and the capital of Telangana is Hyderabad. And my university is a central university. Central university means funded by Government of India. So there are different types of universities in India. Central government funded, state government means province funded, private universities, and all this. So among them, central government funded universities have good quality of research because they don't have any problem for this money and all this. So this is our University of Hyderabad, and it is a central university. Recently, we are awarded with the Institute of Eminence from Government of India for 5 years. So Institute of Eminence means central government will give some money for 5 years to develop basic research, hostel, faculty, all the infrastructures. So for 5 years. So we are ranked 4th among the Indian universities, and we have a very big campus of 2,300 acres, and mostly our students are master students, and we have more than 5,000 students. So this is our Institute of Eminence logo. So these pictures are from our university only. So actually our university is located in a deep forest when it is established. Now almost the city came towards the university, and we are surrounded by a very big city. So when the university is established 45 years ago, so it is established far from the capital city, and far means 40 kilometers away from the capital city, and it is among a big jungle. So we have a check dam, we have peacocks, deer, wild boars, many animals. So this is the lake, this is the dam, which is there in our university, and this is our administrative building. So after looking into the university, so what actually is of my interest for research? So I work on different research materials. It arises from my PhD itself. Why? Because my BSc, MSc is in electronics, and my PhD is in material science. So I'm doing both these electronics and material science together, and this is how I got involved. I am working on magnetic sensors. So it is my oldest research. I work on giant magnetoimpedance, flux gate, tunneling magnetoresistance, planar Hall resistance, all these different sensors. So even now, we are working on field effect transistor biosensors. So my other research is 2D material metal nanocomposites. So metal nanocomposites plus 2D material mixed together as a nanocomposite. So we have observed spin glass behavior in graphene nickel ferrite, and we formed a graphene ferrite. So we observed it for water purification applications, antimicrobial activity, and all this. We prepared graphene manganese ferrite. So we will use it for adsorption, antimicrobial, checking water purification and all this. And currently I am engaged in sodium ion and lithium ion battery materials. Means we are focusing on electrodes and especially anodes. So we also work on multiferrites, so bismuth ferrite, doped bismuth ferrites, composites, both in nanopowder and thin film form. So I'll speak about battery materials in this talk. And after the battery materials talk is completed, I'll give a small extension about what is about my magnetic sensors. Just a glimpse. So this is the problem statement. So we all know that lithium-ion batteries are heavily being used in consumer electronics and everywhere. Nowadays, electric cars are there. So the Tesla, so it uses lithium-ion batteries. So electric bikes, electric cars, our laptops, mobile phones, whatnot. Each and every electronic gadget now uses lithium-ion batteries. And you all know that lithium-ion batteries are very scarce and we need to enhance the existing capacities. So to achieve high energy and power, metal oxides are used as anode materials. So currently you all know that graphite is being used as anode material, and this graphite is having theoretical capacity of 370 mAh per gram, and we want to enhance that capacity. So for enhancing that capacity, so metal oxides are being used. So metal oxides are called as the conversion anodes, and they show enhanced storage capacity. So compared to the conventional carbon anode materials. So among these metal oxides, cobalt ferrite is a promising anode material for lithium-ion batteries. So why? Because so it is having high chemical stability and comparatively it is of low cost. Comparatively it is of low cost. So when we identified the advantages of this material, so we felt like we should also know the drawbacks of this material. So the drawbacks of this material is high capacity fading. High capacity fading means you all know. So when you buy a mobile phone and when you charge it completely, so the charge will come for 2 days. And it will be same, the behavior will be same for maybe 1 month, 2 months, 3 months. So after that, when you charge it, the mobile phone fully, the charge will come only for 1 day. And once the phone gets older, so it is like, so you charge in the morning and afternoon, the battery is 0. So something like that. That is called as capacity fading. So capacity fading is because of the conversion reactions. So to overcome these problems, researchers have made composites with carbonaceous materials, means graphene and metal oxides mixed together. So then capacity fading might be decreased. So here we are studying about cobalt ferrite and cobalt ferrite mixed with reduced graphene oxide. So we want to check how reduced graphene oxide with cobalt ferrite mixed together will work as an anode for lithium-ion batteries. So porous cobalt ferrite with different concentrations of graphene is synthesized by solvothermal method. Means since we want to check the effect of graphene, what we thought is like, look, we'll make the composite of RGO plus cobalt ferrite with different percentages. So first of all, 10% of RGO, 90% of cobalt ferrite, 20% of RGO, 80% of cobalt ferrite, 30% of RGO, 70% of cobalt ferrite, 40% of RGO, 60% of cobalt ferrite. So we made 5 different samples and tried to check how it behaves. So the prepared cobalt ferrite materials, they were characterized using various techniques like XRD, SCM, FTIR, Raman, TGDTA, and all these to check whether they have formed correctly or not. So it is for structural confirmation. And once we have confirmed the structure, so the electrochemical characteristics were studied using cyclic voltammetry and galvanostatic discharge materials. So among all these composites which we have prepared, 20% RGO plus cobalt ferrite showed very good electrochemical performance and very good reversible capability and excellent cycling performance. So this is the one which we are talking about. Now, so this is cobalt ferrite. Cobalt ferrite possesses high theoretical capacity, 914 mAh per gram, but it suffers from capacity fading. So when we are saying that it is suffering from capacity fading, what we thought was we can add a binder into it. So we added a sodium alginate binder into this porous structure. And we want to increase or enhance the performance of lithium-ion batteries. So this is the synthesis method. So this is the graphite, and we are preparing graphene oxide by modified Hammers method. And using the solvothermal procedure, we are adding the metal precursors, ethylene glycol, and all these. And we are preparing cobalt ferrite anchored on graphene sheet. So this is reduced graphene sheet and cobalt ferrite on it. Reduced graphene sheet, cobalt ferrite on it. So this is the schematics of synthesis. So graphite to reduced graphene oxide is obtained by modified Hammers method. And from modified Hammers method to composite of reduced graphene oxide and cobalt ferrite is obtained by solvothermal method. So these are the structural characterizations of this is black one is pure cobalt ferrite, red one is cobalt ferrite with 10% RGO, green one is cobalt ferrite with 20% RGO, blue or purple one is cobalt ferrite with 30% RGO, and this one, this color is cobalt ferrite with 40% RGO. So here, the peaks have exactly matched the JCPDS data. So the observed crystal structure is cubic, and the crystallite size is characterized using the Scherer's formula. Beta cost size is equal to lambda k by d. So the calculated crystal size of this porous sample is found to be 45 nanometers. And when we check the SCM, so it is almost the same. So SCM has confirmed the calculated crystallized size. So we calculated using this formula. So this is the FTIR data. So the black one is pure cobalt ferrite. The red is cobalt ferrite with 10% RGO. The green is cobalt with 30% RGO. So, sorry, I think, right? Yeah, black is pure one. This is 10% RGO with cobalt ferrite. This is 20% RGO with cobalt ferrite. This is 30% RGO with cobalt ferrite. And this is 40% RGO with cobalt ferrite. So you could clearly see that so the peaks are prominent and they are being shown. So there is a peak at 1580. So this 1580 is a characteristic peak of stretching vibration of the unoxidized carbon backbone. So there are bands at 3380. So where is this 3380 and 1349. This is 1349. So these bands at 3380 and 1349 can be related to OH stretching and deformation vibrations. There are also bands at 1209 and 1083. So they are CO and COH stretching groups. So the absorption peak is also observed at 584. This is the absorption peak. So this belongs to the cobalt ferrite MO bond. So using all these techniques, we have confirmed that cobalt ferrite is exactly formed. But how do you confirm the graphene? So you confirm graphene only you believe that there is graphene in it. So look at it. The black one is cobalt ferrite with 10% RGO, and red is cobalt ferrite with 20%. Green is cobalt ferrite with 30%. This is cobalt ferrite with 40%. So all the peaks means we haven't checked bare cobalt ferrite. Only we checked with all these 10, 20, and 30. So all these show that there is a graphene concentration here, and the graphene peak kept on improving, and it is showing prominently as the concentration is increasing from 10 to 40. So this clearly shows that so our composite is graphene with cobalt ferrite. Now these are our SEM images. So if you look into the SEM images, this is pure cobalt ferrite, 10% with cobalt ferrite, 20% RGO with cobalt ferrite, 30% RGO with cobalt ferrite, and 40% RGO with cobalt ferrite. So you can see that they are spherical particles, and you see that this is the graphene layer. On the graphene layer, they are anchored onto the graphene layer. So this is the graphene layer, you can see. So this is how the morphology looks like. And when you take the EDS of the sample, so you see that Fe, CO, O, Fe, CO, Fe, CO. So there are no impurities, and the sample is formed in a pure form. So these are the HRTM images. I don't know whether you can see them clearly or not. I'm seeing some lines around it. So I'll skip this one and I'll go to the next slide. So this is the HRTM images. So look at the HRTM images. So these are the particles, and this is the SAED pattern, and they clearly show that. So look, this scale is 20 nanometers, and our particles are approximately of this length. So we have studied the electrochemical properties. So the electrochemical properties means we made it into a coin cell. So you might have saw the coin cells, right? Maybe in your batteries or in toys, there will be coin cells. So CR202, CR204 coin cells will be there. So we prepared a coin cell and we checked the electrochemical properties using cyclic voltammetry. So this is for pure cobalt ferrite. This is for cobalt ferrite with 10% RGO. This is for cobalt ferrite with 20% RGO. This is cobalt ferrite with 30% RGO. This is cobalt ferrite with 40% RGO. So these samples show the cathodic peak located at 0.04 volts. Look at this one, 0.05 volts. So this is the cathodic peak. And so this is showing good cycling capacity. So look at this cobalt ferrite with 20%. So in the previous case, we found that this is the good sample. So since this is the good sample, in order to avoid the capacity fading, whatever we planned earlier is adding some binder into it. So this sample, the C, is added with sodium alginate binder, and it is being brought into the CV again. So when it is brought into the CV again, you can see that it is occupying large area. So when it is occupying large area, it means that it has very good capacity. So this is about discharge capacities, and so discharge capacity with cycling number, specific capacity with voltage. So what is happening is like, so that this is the discharge capacity. Discharge capacity means that, so we apply 0.1 ampere of current, and we observe the charging, and after that we leave it, and we see that how it is discharging. So if you look into this diagram, so pure cobalt ferrite is this one. This is the pure cobalt ferrite. So it is charged up to 800, and then after 20 cycles, or after 30 or 35 cycles, the capacity came down from 800 to 200. So charge capacity means the amount of energy the battery stores. Cycles means, so if you charge for one time and if you discharge for one time, so that is called as one cycle. So pair one, you see that, so the charge capacity decreased from original 800 to somewhere around 300 in 35 cycles. So after 35 cycles of charging and discharging, the original sample is losing a lot of charge. So the red one, this one, the red one is cobalt ferrite with 10%. Cobalt ferrite with 10% is initially showing good charge, but only after 15 cycles it is coming back and it is losing all its charge. So look at the orange one, cobalt ferrite with 20%. So orange one, cobalt ferrite with 20%, this one here. So it is showing a capacity of 1000, and even after 50 cycles, it is stable, means it is not leaking. It is regaining its own capacity. So it is regaining its own capacity and it is really good. So that is why we are using this cobalt ferrite with 20% RGO. So these are the charge discharge curves for pure cobalt ferrite, 10% RGO, 20%, 30%, and 40%. So look at this cobalt ferrite with 20% RGO. They are very clear. And so you look at voltage, 2.5 volts, and the specific capacity is gradually this one. So this is the discharge capacity versus number of cycle plots. So this is cobalt ferrite with 20% RGO with alginate binder. So we are checking with more number of cycles, and initially the capacity is around 1100, and it retained its capacity even after several charge and discharge. So this one. So this is called as discharge capacity. How do we do is, let us say that we are charging our mobile phone. So we are charging our mobile phone, and when you see your mobile phone charger, you might have saw the current rating over there, right? 2 ampere, 3 ampere, 4 ampere, 5 ampere. So what happens if we charge with what you have? Okay, let me say. You might have saw an iPad charger and an iPhone charger. So if you charge your phone with iPad charger, what happens? The phone charges very fast. Why? Because it is having the highest current rating. So in that way, there are several current rating chargings. What we did was we tried to charge our material with, just hold on, let me see. Okay, so charge our material with 0.1 amperes. So then the capacity is around 900. So we double the current. When we double the current, the capacity decreased to around 700. Again, we increased the current to 0.4 amps. So the capacity decreased. So we double the current, the capacity decreased. Again, we double the current, the capacity decreased. So what it's saying is, when you are increasing the current, means charging it very heavily, the capacity decreases. Okay, that is normal. But when we go back to the original current, look at, see, this is 0.1 or 914 here, and again this is 914 here. So when we went back to the original current, then original charge is regained. And that means that even if we use high currents, the material will undergo inferior performance, but it won't lose its property. In some of the materials, what happens is that all of a sudden, if you give high current, the material smashes and it will lose its property. So here we checked that even under high currents, after application of high currents, if we go back to our normal current, this is normal. So this is the importance of this result. And so we made the cobalt ferrite and successfully synthesized it using solvothermal, characterized it with 104 milliamp per gram at 0.1 C, means current rate. So actually we have surpassed the theoretical capacity because we have a binder. Now, of course, this is not the last slide. I'll give 5 to 10 minutes introduction about my research. So magnetic sensors. So magnetic sensors means they are devices where they detect the magnetic field in the ambience and they show the output. So magnetic fields or magnetic sensors find various applications. So in your hard disk, in your computer, read-write storage is done by these magnetic hard disks only. So we can use them as biosensors, fake currency testing, non-destructive testing, marine submarine detection, oil and mineral exploration, space. In all the spacecrafts, there are magnetic sensors, and navigation. So navigation in the sense you might have, you got your mobile phone and you got the map software. Whenever you go to a new place, if you want to go from airport to hotel, so you open your phone and say that, look, how far is it? And you'll get the exact location and how to go and all this. So how do you think it is working? So it is working with a combination of a GPS, Google Maps software, and your phone has 3-axis magnetic sensor in it. So that one is being used for detecting in all this. So we have developed a similar sensor for Samsung during my PhD in South Korea, and we gave it to them. So this is a small definition about magnetic sensor. A sensor is a device that measures the physical quantity and converts the signal which can be read by observer or an instrument. And magnetic sensors means it detects the presence of magnetic field and converts into electrical signal. So advantages of magnetic sensors are contact-less sensing. We don't need to take the object near to the place where detection should be there. It can detect from far away. So it can deliver electrical response often linear to the field, means linear response will get it. So there are different types of magnetic sensors, and I have worked on Hall, GMI, TMR. Now I am working on FluxGate. So we worked for biosensor applications. So how do we apply for biosensor applications? Is we fabricated thin film sensor by sputtering and lithography, and we made a sensor, and we tried to use this sensor for biology sensor detection. Biology sensor detection means generally, you know that so in this COVID, so they might have been using the techniques called as ELISA or the other technique called as PCR, polymerase chain reaction, and all these. So whenever we give our sample, the results will come on the next day, or it might take few hours time. So those are the techniques which take lot of time and highly sophisticated instruments. Instead of that, we want to use magnetic sensors where the result can come out in 10-15 minutes. So how do we do is so something like this. So a magnetic field sensor is here, and let us say that I want to detect malaria. So if I want to detect malaria, I will deposit malaria specific counter biomolecules on the sensor, and I'll take the sample from the patient, blood or serum, and on the blood or on that sample is conjugated with magnetic nanoparticles. So when I conjugate it with magnetic nanoparticles and drop it on the sensor head, what happens is that if there is a malaria specific molecule here, the molecule and counter molecule form specific bonding. They have the nature of bonding bonding that is called as specific hybridization. In biology terms, we call it as antigen antibody interaction. So when they form antigen antibody interaction, they stick onto the sensor surface, and this magnetic nanoparticle will produce a stray field, and this sensor indirectly detects the malaria signal. So this is what we are trying, and we have succeeded up to something. So this is our magnetic biosensors research. So these are a few of my papers. So normally we used to advertise for MSc and PhD whenever I go for seminar. This is always remaining. So of course, if you want, you can. We take international students also. You can pass the information to your students if necessary. Thank you. That's all from me. Thank you very much. Any questions, please?
Thank you very much, Pratap. Nice, very nice seminar. It is usual from you. Your seminars are all so good, and you show for us several news and scientific news. And so, more on time, thank you very much. Congratulations for your talk. And now I will open opportunity to people from our university members of the Latin American network of condensed smart physics and science of materials to ask you one question each one. I will begin for the representative of the Universidade Nacional Maior de São Marcos. Please, go ahead.
Not only this topic, anything related to my research interest, you can ask.
Thank you. Who is the representative of São Marcos, please? Okay. Then Albino from Universidade Federal de Pernambuco. Can you ask your speaker?
Yes, sir. Thank you. Pratap, sorry. Congratulations for a very nice talk. And I have two questions. Yeah.
Yes, please.
Please, with this graphene iron oxide nanocomposite, did you study the possibility of using it for cancer treatment?
Using it for? Can you please repeat?
For cancer treatment.
So cancer treatment.
At least to me, not for Albino. Albino speak 3,000 language. Anyway, thank you very much again, Pratap. And but I would like to open opportunity to, if you let me see. James, do you have any question for us? James, are you present? James Godesh.
Profesor, buenos días, profesor. Saludos, profesor Isaías.
Salud.
Profesor Pratap. Por aquí no hay preguntas del público. Felicitaciones por la...
Okay. Ítalo, do you have any question for Professor Pratap? Ítalo, are you present? Bueno. Si tenemos más alguna pregunta, puede hacer ahora, o si no, nosotros vamos a terminar la sesión. Bueno, agora eu gostaria de agradecer às universidades participantes da rede de Física da Matéria Condensada e Ciências de Materiais, composta pela Universidade Nacional Maior de São Marcos, Universidade Federal de Pernambuco, Universidade Federal Rural do Rio de Janeiro, Universidade Nacional de Colômbia, Cinevast, México, Cinvestat, México, e Universidade Nacional de Barranca. Now, I give the opportunity to our invited speaker to finish this session with your nice, with your the word with you, Pratap. Pratap.
Yes, Professor.
The word with you, you can see for speak for us your last words.
Yeah. Okay. So respected all professors. So thank you very much for patiently listening to me. So in the field of these magnetic sensors or nanocomposites or multiferroids or anything, so I'm looking for collaborators where we can work together, maybe by a joint project or whatever it may be. So if you have any opportunities like that, so feel free to contact me. So my email ID is already known to you. So it is pratapk@uohod.ac.in. So because basically I'm very much interested in research and I love meeting people. I travel long distances. I met Professor Isais in 2016. So it is not like I will not travel there, I will not travel here, I won't come here, I won't go there. But I love interacting with people. I love working together because when we work with different people, different groups, good ideas will come out. So it is not always with, if I work with MIT, there will be best results. So that is my ideology. So if you have any similar research interests, anything, so you're welcome to talk to me. Thank you for giving the opportunity, and I'm very grateful to speak with the great professors. Thank you very much.
Thank you very much, you, Pratap. And las personas que están presentes pueden abrir su cámara para nosotros agradecernos al profesor Pratap. Por favor, abran sus cámaras y vamos a saudar al profesor con una salva de palmas.
Gracias, Pratap.
Thank you.
Thank you.
So, more one time, thank you very much, Pratap, again. And now is finished this session.
Thank you, Professor.
Thank you. See you
Thank you very
around.
much.
Thank you.
See you
Thank you.
around.
Thank you. Thank you.
See you next meeting.